Let's see, yeah, Amira, if you have more followers than Matthias Troyer yesterday. Let's wait another 10 seconds and then we start. Okay, we waited a minute. I think we can slowly start. Let me find my Zoom again. Voila. So good afternoon, everyone. Welcome to the NITheP Mini-School on practical programming of quantum machine learning. My name is Francesco Petruccione, and I have the pleasure to introduce the lecturer again, who is Amira Abbas, who is a very famous PhD student and quantum computing advocate. Yeah. And today, in her last lecture, she will address, if I remember correctly, the very famous problem of the Barren plateau. Yeah. So that we will move from the very beginning in very elementary approaches in the first lecture to what is a problem of relevance to current research. Yeah. And as after the second lecture, after this lecture, when the Zoom meeting is over, a new quiz should pop up in your browser, and you're welcome to take the simple quiz, and we will use the quiz to award the certificates of participation. So Amira, thank you very much for being with us again today, and we are very much looking forward to the last lecture in this school, and I hope this won't be the last time you offer us a mini school. So maybe in the near future we can plan another one. Yeah. So Amira, over to you. You're welcome to share your screen. And while you do that, please a reminder to use the Q&A facility to ask your questions. And like in the other lectures, Ilya will moderate the question and answer session. Amira, thank you very much.
Cool. Thank you so much, Francesco. Yes, so welcome back, everybody, to the final talk of this mini-school series for basic programming for quantum machine learning. And I want to just start off by saying, thank you to all of you for attending, and the feedback that I've been receiving from these talks have been really great. I'm very happy to see such wonderful things like people writing blog posts about the talks and messages that I've received. And I apologize if I haven't had the chance to get back to you as yet, but please feel free to email me and ask me anything. I'm a lot better at responding via email. But yes, thank you so much for participating, and I hope that we do something a little bit more advanced, building off of these topics that we discussed now. Maybe in a couple months' time, we'll do like another school similar to this on quantum machine learning. Okay, so yes, as always, feel free to interrupt and ask questions as much as you like. I think that this talk I anticipated to be a little bit shorter than the others, so that we can have more time to discuss things and brainstorm ideas, maybe explore new concepts and topics, because we are definitely now going to enter a little bit of uncharted territory with quantum machine learning and discuss some of the problems that come up in some of the models. So feel free to ask as many questions as you like, and then we will also go through a notebook at the end. So previously in the last lecture, what we covered, I just want to remind you, was we discussed a little bit of how some quantum models can look, right? So I think we mentioned support vector machines and how these can be enhanced by quantum computation. We spoke about quantum neural networks very superficially, and then we also went a little bit deeper into this idea of a variational quantum classifier, and we coded this up as well. I did receive some messages saying that the notebook is not on the NITheP website as yet, but we'll make sure that that goes up soon if it's not already there. And then today we're going to finally talk about this problem of barren plateaus, right? So I will explain what this means, and then we'll go into just quantum neural networks again, because these barren plateaus are an innate problem that come up in quantum neural networks in particular. Then I want to plant a little seed in your head about the idea of loss landscapes and what this means in a classical model versus a quantum model. And then lastly, we'll demonstrate the barren plateaus phenomenon using PennyLane. So there is a tutorial that's already coded up and beautifully presented on the PennyLane.ai website. And I just basically steal this tutorial and take you through it. Okay, so quantum neural networks. If you remember from the last talk, I put up a few papers that have different proposals for what quantum neural network models look like. And I think loosely speaking, they all kind of incorporate a variational architecture. And a lot of the times, all people mean in their papers, in their research, when they talk about a quantum neural network is actually just a quantum variational classifier. So the terminology is very loose. There are other proper definitions for quantum neural networks that have different structures to the variational classifier. But for today's talk, you can loosely think of quantum neural networks as this kind of framework and model here. So just simply a variational classifier, where we discussed, I think, in the second lecture, how one can encode classical data into a quantum state through some feature map. And then after this feature map is applied, you have a variational model in your circuit. So some parts of your circuit that depend on some parameters that need to be trained and optimized. And then we extract some output from this circuit, from this model, through some measurements. And then we map these measurements to a probability distribution over labels or outputs. And it doesn't always have to be a probability distribution, of course. And yeah, so this is just the framework for this quantum variational classifier, which I also now refer to as a quantum neural network. So also just, I think when you're reading literature, be cognizant of the fact that the terminology is quite loose. And so when one defines a quantum neural network and a quantum model, there are different things going on in there. So just pay attention, I think, to the specifics of the paper that you read or the book that you're reading. Okay, so if you remember, then I also made this comparison to linear neural networks, right? So quantum circuits in this setting here can also be directly compared to a linear neural network, right? Because a linear neural network, we can write it quite simply as like this product of weight matrices on our inputs, which is typically in a vector. And if you want to inject some nonlinearity into your quantum model, then really this nonlinearity, the source of nonlinearity has to come from your measurements, right? So trying to inject nonlinearities in this structure here, in this circuit, is very unnatural and very difficult for a quantum computer to do. So really the tricks that one needs to employ to inject some nonlinearity has to come from the measurement. And I very much like this picture here that's taken from this paper, Circuit-Centric Quantum Classifiers. And you can see the direct comparison between this quantum circuit idea and a graphical representation of it. So you start, of course, with some state preparation. And what the state preparation does is it takes your data and it maps it to some feature mapped space, right? So typically a high dimensional representation of your data. Then you apply the model circuit, which depends typically on some parameters. And you can think of this model circuit as like the linear layers in your neural network. And then you do a measurement, which is like the nonlinear layer part. And then you can do some post-processing, which we discussed in the last talk. We discussed a few ideas like computing the parity of an output bit string and how to map this to a probability distribution over your labels. So there's other options here as well, so like a simple thresholding function and so on. So this is a nice idea of how to think about these quantum neural networks classically. And what I want to now go into is then just to remind you about how classical optimization is done of these classical neural networks, right? So typically when we have a model, a neural network, and we have these weight matrices that connect our inputs to our hidden layers, and then our hidden layers to each other, and then eventually to an output, one has to optimize these weights, right? To give us a robust prediction or output. And how one does this is there are many different ways to do optimization over neural networks, but a very successful technique has been through gradient-based optimization. So the first step in this whole gradient-based optimization technique is to basically start with some sort of first guess for your weight matrices. So you guess the parameters in your model, and then you compute the label, the output. So there's y hat here. And this gives you a prediction for a certain data point. So if, for example, your data is, let's say, pixel values, and now you want to classify if it's a cat or a dog, then you guess the weight matrices, the parameters in your model, and then it gives you an output that says it's a cat, for example. And then you take this predicted output from your model and you plug it into a cost function. And a cost function takes in your prediction from your model, so your y hat, and then it basically checks in a supervised setting, it checks your prediction against what the true label was. So in a supervised setting, you have data that has true labels associated with it. And so it checks it against the actual label. The actual label says it was a dog, so your model got it wrong. And so now you have to go back and change the parameters so that your model can start to lower your cost and give you correct predictions. So a typical cost function, for example, is something very simple like the mean square error, where you can write it like this, right? Your prediction value minus the true value squared. And you can see that if these things are very close together, then your cost is going to be a smaller amount than if these things were very far from each other, then your cost is going to be quite high. So this cost function intuitively makes sense, right? Because it penalizes your model for very wrong predictions and awards it, in a sense, for predictions that are close to being correct. And importantly, this cost function needs to be differentiable. And the reason is so that we can start to use gradient-based optimization techniques. So in some of these gradient-based techniques, what is typically done is you take your cost function and you compute the derivative of the cost function with respect to the parameters in your model. And this cost function, this derivative of your cost function, then gives you some information, some useful information on how to update the parameters in your model such that you can lower the cost and get accurate predictions. So a very common algorithm in classical machine learning is just something called gradient descent. It's a rule on how to update your parameters such that you lower your cost and you get robust predictions. So gradient descent can very simply be written in this line here, where you basically say you update your parameters by taking your old parameters and then you subtract this constant times by the gradient of the cost function with respect to the parameters. And this constant here, this eta is something called the learning rate. So the learning rate decides how big a step you want to move, multiplied by this derivative of your gradient here. And this is something you choose, right? So this is a hyperparameter in your model, something that you decide on and you fix. And basically you keep doing this, right, until you find an optimal parameter set, theta star, let's say, and this theta star then gives you a very low cost value. So if we remember, like in the first talk, I think we put up this plot. This is essentially what we're trying to do with this gradient descent algorithm. We're trying to find this theta star here. If this is our cost function, just naively plotted like this, we're trying to navigate through all the different parameters that we can possibly have, such that we pick one set that minimizes our cost function. And why do we want to do this? Well, by minimizing our cost function, we start to get robust predictions for our model, predictions that are very close to the training data that we have. Okay, so are there any questions? I just see one, but I don't know, should we take it now?
We can take it, but I think it's more generic question, and if you want to answer, yes. Would you feel that the quantum partial derivatives for a super polynomial solution will somehow work towards the optimization of quantum machine learning?
I have no idea. So I'm not even sure what that means, but yeah, I don't know. Ilya, if you know the answer, please feel free to step in.
I also don't know what is a super polynomial solutions.
Yeah. I'm sorry, I don't know, but I mean, message me privately and we can talk. Maybe you can explain to me what you meant by this question. But yeah, sorry about that. I don't know.
Okay, and there is one more question. And from where do we obtain the value of y? And when we have a multiple parameters like theta 1, theta 2, we will be doing the chain differentiation or product, or partial differentiations?
Yeah, sorry. So that's a very good question. I've been kind of abusing notation quite a bit here. So I write like θ1, θ2, but this is not right? So this is actually a matrix here, and you're totally right. So this gradient here will be a gradient of a cost function with respect to every theta. So it will be a vector. You can think of it as a vector with every element being a gradient, a partial derivative with respect to each parameter theta. So θ1 all the way to however many thetas you have. So yes, so that's correct. And I have not been very good with notation. So please do bear that in mind, that this is typically a gradient vector. Yeah. I hope that makes things a little bit clearer, but if not, then I think it will become a little bit clearer towards the end where I explain or write down this matrix or this vector. Okay. Okay, cool. Yes, and the chain differentiation, we will talk about that in, I think, the next slide. Okay, so a big problem now so these gradient-based techniques were exciting, and now we finally have, these big, powerful computers that can handle these kind of computations, right? And so then people started building neural networks and optimizing them using these gradient-based techniques. And then they started to run into some problems. And two of these problems are that the gradients, they either start to vanish or they start to explode. And what do I mean by this? So if we go back to this gradient descent updating rule, right? If we look at what this thing means here, this is the derivative of the cost function with respect to the parameters in your model. And if we have a neural network, as I was saying just now, like, there are lots of parameters in this neural network, and how one calculates the derivative with respect to each of the parameters in the model is calculated using the chain rule. So there is a nice, I see the reference is not here anymore. Oh, here it is here. There's a nice resource here, just a blog post on understanding backpropagation in classical neural networks. So I won't go too much into this, but you can read about it there in this blog post. And basically, all you have to remember, or all you have to think about, is that by using the chain rule in a neural network, you're essentially like going back into this network. And remember, a neural network is just like, you can think of it as stacked functions, right? Because you have some multiplication, some nonlinearity, and then some multiplication, some nonlinearity. So it's like linear models with nonlinearity on top of it stacked together. And then when you want to calculate partial derivatives with respect to every parameter, you need to use the chain rule to get to each of these parameters to calculate the derivatives, right? And when you do this, if you have derivatives that are, or values that are very small, then when you multiply over all these small values, right, in your network, then your gradient values are going to vanish, okay? Because you're multiplying by small numbers, a lot of small numbers. And on the other hand, if you have numbers that are very large and you multiply over this large chain of large numbers, then your gradient estimations are going to explode. And these are things that come up in certain neural networks that you design classically, and it's called the vanishing and exploding gradient problem. And so this was really bad, of course, because if you think about this formula again, right, if these gradient values here are vanishing, they're essentially zero, let's say, then you're not really updating your parameters anymore, because now this term is zero, and then your old parameters are just staying the same, and you're not moving in your parameter space anymore. So this updating rule becomes a little bit meaningless. And on the other hand, if you get these massive values here, these gradients are exploding, then this updating rule becomes very unstable. Your network outputs very unstable results, and so then your model also doesn't converge and train very well. So this was a very big problem, and thanks to all the amazing machine learning researchers out there, there are now several techniques that are proposed, very well-established techniques that are proposed to combat these vanishing and exploding gradient problems. So the first one is something called gradient clipping, which, as the name suggests, you literally can clip or cap the maximum gradient value that you have as you do backpropagation through your network. So you literally say, like, this is the maximum I want my gradient value to ever be, and you clip it. And this is just a simple, silly picture that just shows that like with clipping, you can then get to a minimum cost value. Whereas without clipping, these gradient estimations like blow up and you never really kind of go to this minimum space here. Another very popular suggestion in literature is something called weight regularization. So I just stole this picture, but I mean, this is different notation, but you can think of these weights as the thetas that we had previously. And then you just add some penalty term here, some term that depends on theta to penalize it if it gets too large or if it gets too small. And so you kind of regularize your weights by adding some regularization term when you update. And then I think the one that makes the most sense to me to avoid these problems is just to simply avoid certain activation functions, right? So when you're computing derivatives in a neural network, you have these nonlinear functions that are in there, right? And so examples of these nonlinear functions, these activation functions, are like the tanh function. So the tanh is this blue line here. And when you compute the derivative of the tanh function, then the value lies between 0 and 1. And so if you have lots of tanh functions stacked on top of each other, this is always, when you do the derivatives, it's always going to give you a value between 0 and 1, and then you multiply these small numbers together in this chain, and then your gradients are going to vanish, right? So if you switch out the tanh function for a different activation function, and there are now very popular ones like ReLU and leaky ReLU that are specifically designed to avoid this kind of problem, then you can avoid these vanishing gradients in this kind of setting. So this is another nice way to do this. And then, of course, there is, I mean, one can just redesign your network, right? So you can, instead of having a very deep network with lots of layers, then lots of hidden layers, then you can just create a shallow network, and you should not have the problem of these exploding or vanishing gradients. But of course, one prefers deep networks, right? Because they work really well and they can approximate functions, lots of different functions better. So maybe this is not, shallow networks is not such a great way to do this, but I'll tell you why I introduced this a little bit later. And then there's also proposals for entirely different neural network structures. So residual networks now are relatively new and extremely successful. And residual networks incorporate things like skip connections. So what do skip connections mean? Instead of having all your weights connected to your first hidden layer, for example, and then the next set of weights connected to the next hidden layer, you can have weights that skip hidden layers and connect to the one after, for example. So you don't have all-to-all connectivity at every layer in your neural network, but you have skip connections. So weights that can connect your inputs to perhaps a hidden layer further down in the neural network. So the way information propagates through your network is a little bit different in a residual network, which is quite interesting because you can have information from early on in the network that comes through later on in the network in a different way. So the information propagates differently. And these residual networks have proven to be extremely interesting and extremely useful. So I think I have a picture. No, I don't. I think it will come later. So I'll show you a picture of why these residual networks look and work so well. Okay, so if we now go back to the concept of quantum neural networks, right? So we're still in I'd say still in a very early phase where we're trying to understand, firstly, the first question is like, can we get gradients from our quantum circuits, from these quantum neural networks? Luckily, thanks to the parameter shift rule and a few other papers, we know that we can, right? So I think I spoke about this in the first lecture, that we can definitely get gradients out of these quantum neural networks, and we can use them for gradient-based optimization. But then the next question, of course, is that once we get these gradients out of certain quantum neural networks, are there any problems that we can run into, like the problems of vanishing gradients or exploding gradients in the classical setting? And if this is the case, if we have these like vanishing or exploding gradients, then we can't use gradient descent rules like this anymore. And so Barren plateaus is exactly one of these problems that we have now found that quantum neural networks suffer from. And so this is what I want to introduce to you today, and make you aware of this, and also just remind you that there are potentially many more problems or issues that we could also face. So really, this is still quite an interesting area of research. Okay, so are there any questions before we go into Barren plateaus?
Yes. So
Okay, cool.
there is a question about the gradient calculation. Is the gradient calculated theoretically or by varying each parameters one by one for the partial derivative?
Yeah, so the latter. So I'm assuming you mean the calculation of the gradients for quantum circuits, right? So yes, unfortunately, this is still how it's done, where you have to vary each parameter one by one. And I think this is like kind of an annoying thing that happens with the automatic differentiation packages proposed. So like PennyLane, for example, is one of them. And I encourage you to go and read the source documentation of how they do their gradient-based calculation. But now they also talk about being able to parallelize these gradient-based calculations if we have multiple QPUs, so quantum processing units. So there could be some parallelization, but yeah, we have to vary each parameter one at a time and then calculate the difference and use that as the gradient estimation. Yeah, good question.
Okay, and I think, yes, you've done a mistake, Amira, by not writing explicitly what the kind of the back propagation when you calculate the gradient means, because there is one more question which is asked, which is coming from the confused person. How
no.
are we
Okay,
saying
yeah.
that the gradient values are getting multiplied with each other? Do we refer to the matrix multiplication of weights with the input data when the weights becomes very small numerically?
No, so I literally just mean, so okay, so I would advise reading the blog post that I put up, but I literally just mean the chain rule. If you write out the chain rule, right, it's a product, you're going to get a product of functions. So if you want, let me go back to this picture. If you want a derivative with respect to this first weight here, then you have to apply the chain rule, because there's another function here that takes in the weight, the first weight, and you have to apply the chain rule as you back propagate through your network. And the more hidden layers you have, the more activation functions you're going to have in your network. And so the more times you have to apply the chain rule, basically. So you're going to have more multiplications of numbers, and you have to calculate the derivatives of each of these functions by applying the chain rule. And if these functions are things like tan H functions, then these numbers, these output derivatives, are going to be small numbers. And so that's what I mean by a series of multiplication of small values. So yeah, I hope that makes a little bit more sense. But if not, these slides will be posted, and the blog post, I think, will answer your question in much better detail than what I've just done.
Okay, thank you. And is there any benefit from superposition for parallelization?
If you mean parallelization of calculating the gradients of the circuit, then unfortunately not, right? Because remember, we have to calculate, how we calculate the gradient of the circuit is we perform a measurement. So any form of superposition is kind of destroyed or not, is gone. And we make a measurement, and then we change the parameters by a small amount, and then we make another measurement, and then we take the difference of these two circuit outputs to calculate the gradients. So unfortunately not, if that was your question.
Probably okay. That was the question, yes. So let's keep going. Thank you.
Cool. Oh, cool. Thank you. Okay, so now we can finally talk about Barren plateaus. Okay, so spoiler, Barren plateaus is vanishing gradients problem, but the reason they occur is for a totally different reason than in the classical setting. So the Barren plateaus result can be found in this paper here by Jared McLean and a few others. And what they find is that if you have a circuit, a quantum model of a particular form, then you run into this vanishing gradient problem. So the circuits that they look at, the class of circuits that they talk about and address in their paper, look like this. So they start with some RY rotations, right, by some angle, pi over 4. And then after these RY rotations, you have a series of entangling layers, right? So these are controlled Z gates between pairs of qubits. And then after these controlled Z gates, then you have some more single qubit operations. And if these single qubit gates are sampled at random and their parameters are sampled at random as well, then this is the class of circuits that we consider. So what do I mean by this? Well, if we just have some arbitrary single qubit rotations here, and then we sample from X, Y, and Z rotations. So we don't specify what rotation, but we just have this as a random variable. And I've just plotted an example of one such combination, right? So this is RY, RX, but essentially these are random. And then also the angles in these gates are sampled at random, uniformly at random, okay? Then what they show in their paper is that these types of circuits, when you try to calculate the gradients of the parameters, then the gradients start to vanish. They go to 0, and the variance around the gradients also start to vanish exponentially. And as we start to add more qubits to this circuit, then this is when we really see this problem magnified quite a lot. So I think this will make it a little bit clearer once we go through the code, but I just want to remind you also, like, remember the variational circuits and models that we were considering in the previous talk kind of looked like this, right? Where we had some RY rotations, some entangling layers, and then we had more rotation. So as we start to increase these models, then a lot of the quantum neural networks proposed in literature today have circuits that approximate these kind of Barren plateau circuits. And this is really problematic, because then when we start to calculate gradients, then we're going to need something better, right? Because these gradients are going to 0 and they're not going to become meaningful anymore. And so this will be a little bit clearer, I hope, by taking some of the pictures from the paper. So what you're looking at here is a graph that has the number of qubits on the x-axis here. And as the number of qubits starts to increase, what's on the y-axis is the derivative of your cost function with respect to one of the parameters in the model. And this is the variance of this derivative. So you can see that the variance around your derivative of your cost function starts to go down very quickly as you start to increase the number of qubits in your model. And if this happens, then the gradients are going to become concentrated around 0, and this is really problematic, because if this goes down exponentially, then you're going to start to require a lot of precision to estimate your gradients, right? So that you can figure out how to update your parameters. And this precision, this required precision, grows so much, like you need so much, like such exponential precision, if I can say, that it removes any form of quantum advantage. And this is a really big problem, of course, because if we just then look at this updating rule, now we have these values here that are going to 0, and how do we then use gradient-based optimization to figure this out, right? So this is really problematic, and the reason that this kind of occurs is because you can think of it as like a concentration of measure phenomenon, right? So as we increase the dimensionality of the circuit, then values start to become like increasingly concentrated around a very small band here. And we're still kind of, I think, figuring this out. And there have been some really great methods introduced to try and avoid Barren plateaus. So I just want to bring to your attention a few of them, and also point out that I think that we still have quite a way to go to understand how to fully avoid these problems that occur. So the first one is from this paper here, and it simply implies introducing some sort of structure into your circuit. So instead of just having all your parameters completely sampled at random, let's fix some of them and then sample some others at random. And so then they argue here that the strategy can avoid Barren plateaus with certain guarantees. And then there's a very nice paper that came out that showed that actually also Barren plateaus, the likelihood of their occurrence, or how soon they occur in your circuit, in your model, also depends very heavily on the type of cost function you use. So the type of measurement operator that one has, this influences how quickly one experiences a Barren plateau. And this paper was published by the group of Patrick Coles. And I just wanted to put here a link to a talk that Patrick Coles is actually giving tomorrow at, I think, around 5 p.m. South African time. And this talk is actually on Barren plateaus, and he will definitely go into a lot more detail on what this is from a technical point of view. And so if you're interested, especially if you're a physicist, I encourage you to to watch his talk, because I think it will be a lot more up your alley. And his group are quite instrumental in trying to understand how to avoid these barren plateaus issues. So they suggested, they published this paper and also a few others around barren plateaus. Okay, and then there was another very recent paper that came out earlier this year on the idea of trying to use higher order optimization techniques to avoid barren plateaus. So what they tried to do in this paper was to try and characterize something called the loss landscape of quantum models. And so the loss landscape is, I've been using the word cost function a lot, but cost and loss functions are interchangeable terms in machine learning, right? So if one talks about the loss landscape, they're talking about how the cost function looks. And remember, you always want to minimize this cost function. So you want to find the global minimum in this cost function or this loss landscape. And in higher dimensions, this loss landscape is really hard to visualize, right? Because it's there's a lot of parameters in this loss landscape in your model. So what they tried to do here is they tried to get a better understanding of how this loss landscape looks for quantum variational circuits, so for quantum neural networks. And they argue that by characterizing this loss landscape using higher order techniques, they can avoid going into barren plateaus completely. So what did they try to do? Well, they tried to use something called the Hessian matrix. So remember, I wrote in the beginning, or I mentioned in the beginning, that we try to find the derivative of our cost function with respect to our parameters, and one can think about these derivatives as just this vector with entries that are the partial derivatives with respect to every parameter in your model. And the Hessian is essentially a matrix with the second order derivatives of the cost function with respect to the parameters. And so they argue that one can use optimization, gradient-based optimization techniques using, instead of the first order derivatives, using the Hessian to navigate through the loss landscape to find the minimum and to avoid barren plateaus. And if you think about the Hessian intuitively, what it is it's essentially a measure of curvature of the loss landscape. So it gives you an idea of how bumpy the loss landscape is. And this paper tries to use the Hessian in particular to try and find the global minimum in the cost function and avoid barren plateaus. And they have some very nice illustrations in their paper. They have a toy model that they used, and they plot the loss landscape, and they talk about the spectrum of the Hessian and how one can use the Hessian to traverse through the loss landscape of quantum models. But unfortunately, very soon after that paper was published, again, Patrick Coles and his group came through and showed another very interesting result, that actually once a model is in a barren plateau, and this happens with a very high likelihood, then the Hessian, the values of the Hessian, all the second order derivatives and higher order derivatives as well, start to vanish exponentially too. So the Hessian no longer provides any meaning anymore, and actually you cannot use it to escape a barren plateau. So this higher order optimization method was unfortunately shown to be not successful. And here is the picture that I was speaking about earlier that I said I'll put up later of loss landscapes. So there's a really nice paper that tries to visualize the idea of these loss landscapes, so these cost functions of neural networks in very, very high dimensions, and then plots them in a 2D plot, right? And what you're looking at here is on the left, a model, a neural network without skip connections. So not a residual neural network, which I spoke about, which is a new architecture that performs really well. But after you introduce skip connections and you visualize the loss landscape then becomes a lot more well-behaved and regular, and trying to optimize over this thing and find the global minimum here is far easier than trying to do so here, right? Because you can see there's tons of local minima that one can get stuck in. And so what I want to propose to you is that, this is very well studied and still being well studied classically, but on the quantum side, we don't really know yet fully what our loss landscapes look like. So could they perhaps potentially look like these here, right? With tons of local minima. And if so, then what transformations can we apply to our quantum models such that we can start to make our loss landscape look a little bit more regular and something easy to optimize over. So this, I think, is still a very interesting and open question in quantum models, and it's also still kind of open, I think, in classical neural networks as well, right? So people are still investigating other techniques other than residual networks to try and regularize loss landscapes. So I think this is really, really cool and interesting field to explore. And yeah, so this is just something I wanted to pose to you and make you maybe think about, because we don't fully understand how these look in a quantum setting as well. Okay, so now I jump to the code and show you that Barren plateaus actually do happen, so they are real.
Okay, before you jump to the code, can I ask you a question?
Yes, sure.
Is there any way to perform a gradient using quantum circuits?
Hold on, I just realized that I can't multitask. So the question was, is there, sorry, what did you say? Is there any way?
Is there any way to perform gradient using quantum circuit?
To perform gradients using quantum
Probably to calculate
circuits.
gradient, you know.
Oh, okay. Yes. So I apologize that I didn't include this. So I had a picture from my first lecture, if you go back. So you can set up your quantum circuit such that when you make a measurement, then all you have to do is go back and change your parameter. So if you want to calculate the gradient of one parameter in your quantum circuit, then you do a measurement of this quantum circuit, and then you go back and you tweak the parameter you shift the parameter up a little bit, and then you do another measurement, and then you take the subtraction of these two measurements, and this can be interpreted as a gradient of this parameter. So you can use circuits, you can construct circuits and shift the parameter that you want to calculate the gradient over, and then look at the outputs, and you can extract gradients from these. So yeah, that probably wasn't a very good explanation, but it's called the parameter shift rule. And strictly speaking, it's not just the difference. I think there's also like a 1/2 in there. So it's basically trying to extract from measurements gradients. So yes, you can use circuits to calculate quantum gradients.
Okay, thank you.
Sure. Okay, cool. So now, yeah, I want to just remind you that I did not code up this tutorial at all. So the author is Shanoaz, and this tutorial is taken from PennyLane, and they have a bunch of beautiful tutorials on there on all topics in quantum machine learning. There are also other introductions of quantum neural networks, variational classifiers, and so I really encourage you to go and check this out if you have some time. But I want to just take you through some of the code line by line and just explain to you what's going on in here. I think it's still really relevant, really cool, really interesting that we can actually observe this phenomenon of Barren plateaus and see that it is real, and that we actually do need to figure out a way to combat this. So the first thing we do, of course, as always, is import PennyLane. And remember, from PennyLane, we need to import NumPy, because NumPy is a little bit different for the PennyLane interface. And then I also just import matplotlib for some plots that we will do later. Okay, and then now I just set a seed for reproducibility, and we'll start with just 4 qubits in the first circuit, model. And so the first thing that we need to do is instantiate a device, right? So PennyLane gives us access to a whole bunch of simulators, and also we can connect and plug into other backends and real quantum devices. But for the purpose of today's talk, we'll just again use the default qubit simulator, and we specify that we want 4 qubits in our model. And then what I do here is I specify something called a gate set, right? So remember, in the Barren plateaus circuit, when this problem arises, we sample randomly from different rotations, right? And so what we're doing here is we're just setting up a gate set from which we sample randomly from to apply these different rotations. Okay, and now I want to take you through creating the circuit that will give rise to these Barren plateaus. So we just call it random circuit for now. And in this random circuit, we pass it parameters. We'll also pass it a random gate sequence that it will apply to every qubit. And then we'll also say how many qubits are in the model. And so the first thing that we do in the circuit is we apply those RY rotations to every qubit. So I don't know if you remember from the picture, but the first thing that happens, the first application, or the first, I should say, operation that happens in these Barren plateau circuit are these RY rotations by pi/4 to every qubit. So that's just happening here in this first loop over all the qubits. We're simply just applying this RY rotation. And then we do another loop over all the qubits, and we apply the random gate sequence that we're going to pass to this function. So we apply the random gate sequence, and this random gate sequence contains parameters. And so we just apply each parameter respectively to each qubit. And then we need to do some entangling layers, right? So remember we had those CZ entangling gates between pairs of qubits. And so we loop again over the qubits, and we just apply the CZ entangling layers. And then lastly, we just create an observable that we want to do a measurement over. So what we're doing here is I just call this H, and H, we create it to be of a size 2 to the n by 2 to the n. It's a big matrix where n is the number of qubits. And then we can specify a wire list over which we want to do our measurement on. And so then we ultimately return, after we apply all these operations to the circuit to set up this Barren plateau circuit, we can then return an expectation value over this observable applied to the complete wire list. And the wire list in this case is just the list of all the qubits in the circuit. So let me run that and not forget to run that. Okay, so now we've created our circuit. We have a random gate set that we can sample from. And so now what the Barren plateau's result says is if we had to sample at random from this circuit, so if we had to compute the derivative of this circuit with some parameters and some gates, and we repeat this over and over and over, then the average of those derivatives will be 0, and the variance around those derivatives will also start to decrease and be 0. So let's do that, right? Let's compute that. So if we assume we're just going to sample from this circuit 200 times, so we're basically going to run this random circuit 200 times with different gate sequences and different parameters, all sampled uniformly at random, then we can do that and compute the gradient 200 times. So we'll do a for loop over the number of samples that we want to specify. I just chose 200 here. And then we choose a gate sequence. So this NP random choice is choosing from the gate set that we defined earlier. So remember we defined it as these possible rotations. And then we can wrap our quantum circuit, our random circuit, into a Q node. So I don't know if you remember from the first talk how we wrapped the quantum function into a Q node was a little bit different, right? So we used a decorator function above here to wrap this random circuit into a Q node, but in PennyLane you can also do it. You can do it like this, where instead of using the decorator, you can just do it directly. And I think the only difference is like this is now like a capital Q here. So you can basically tell PennyLane that this random circuit is a quantum object, and this is the device associated with the quantum object. And this device is what we set to be the default simulator earlier. And then we can go and use the wonderful functions of PennyLane and compute the gradients, right? So we can create a gradient function by calling on QML.grad. So QML is PennyLane. And we pass in our quantum object. So it's our quantum circuit attached to this device. And then we specify here this argnum equals 0. What's happening there is we're specifying that we just want to compute the gradient with respect to the first parameter. So we can, of course, compute the gradient with respect to all the parameters in the model, but just for the illustration, I just want to do it with respect to one parameter and show you that the gradient of this parameter on average will be 0, and the variance around it will also be very, very small. So after we instantiate this gradient, this gradient function, we can then just initialize our parameters to some randomly uniformed sample. We just sample randomly uniform, right, for our parameters. And then finally, we can compute the gradient now by applying this grad function. passing in our parameters, passing in our random gate sequence that we define here. We just choose randomly, and the number of qubits. And then we store this gradient that we've computed into this initially empty list that we created here, this grad vals here. So we're doing this 200 times. We're creating 200 circuits with different gate sequences, with different parameters chosen at random. We're calculating the gradient with respect to the first parameter in the circuit, and then we're storing this gradient into a list over here. So then we can print, after we've done this loop, let me run this, and while this is running, we can print the variance of this gradient, and we can also print the average of this gradient. And it has run, and we can see now the variance of the gradients for these 200 random circuits is very small, right? So, and we only have 4 qubits in the circuit, so this is still quite bad. And the average of the gradients of this circuit, the first parameter, is also very small, so also like concentrated around 0. So this is problematic, right, for various reasons, because, and especially when this starts to get more and more close to 0, then we're going to need more precision to estimate this properly. So what's nice and what's interesting about this tutorial is they also now then go and they repeat exactly what we just did here. Let me actually run it because it takes a bit of time to run. They go and repeat what we just did here, but over different circuit sizes now. So for this one, we just did this, and this was a 4 qubit circuit, and we printed the variance around the gradients and the mean around the gradient. And now they're saying, okay, let's do the same thing. Let's take 200 samples and let's compute it over different circuit sizes from 2 all the way to 6 qubits. And then we'll store the variances in this empty list here. And so while this is running, I mean, we can also just talk about what's happening in here, but it's essentially the same thing, right? There's, we're instantiating a device, we're wrapping our function into a Q node. We don't have to repeat all of this, right? Because it's all done earlier, but just for completeness, it's here. And then we're defining our gate set. We're choosing our random gate sequence. We're defining random parameters, we're sampling random parameters. We're calculating the gradients. We're appending the gradient values. And then we're also appending the variance of these gradients as well. And then once that's finished running, we can plot this. So we can actually plot over the number of qubits as they start to increase. We can plot the variance of the gradient on the y-axis. And what we should see, if we are in a Barren plateau, is we should see that this variance around the gradients starts to go down as we increase the size of our model, increase the number of qubits in our circuit. So while this is running, are there any questions?
Yes, there are a couple of questions.
Cool.
Can we take an advantage of quantum tunneling to get rid of Barren plateau problem in variational circuits?
Yeah, it's a good question. I don't know. Yeah, I don't know the answer to this. I don't think so, because I think that's a different phenomenon, and yeah, but I'm not sure.
Yeah, I think I would agree with you, because like Barren plateau is for the cost function, and it's not a kind of Hamiltonian. It's not a barrier which you can tunnel through. So I think it's, yeah. Okay, and another question is from Camille, and talking about the problem of vanishing gradient. I would naively divide by the norm of the gradient to always have a finite quantity, but this might be computationally demanding. As a side comment, this issue of Barren plateau looks a bit intuitive if you have lots of parameters, and if on top of that they are initialized randomly, one would expect that the output of the circuits does not really depend on the particular value of the given parameter, and as a result, the gradient vanishes.
Yeah, so that's not very much a question there, right? Yeah, so the first point, you're right. And I think this is actually what is done with the L2 and L1 regularization. So I think they do divide through by some norm there. So I think you're right there. I don't know about the computational expensiveness or yeah, how expensive that is. You're probably also right there. And yeah, so I think this Barren plateaus thing is it occurs when the circuits start to approximate these T-design circuits, right? And And what you get is this Haar random distribution of outcomes. So you're right, the things just start to be random and don't depend too much on the parameters. But I don't know. Something that also I was wondering is, if the gradient goes to 0, does the circuit output also go to 0? And I think the answer is no, but when you compute the gradients, the outputs are just so similar or so close together, so that the gradient starts to go to 0. So yeah, I don't know if I'm just confusing you more, but yeah, these are thoughts that I had. So thanks for the comments, Camille.
Okay, so there is one more question. What is the objective function here which is getting minimized?
I'm so glad somebody actually asked this, because this is a very good question and something that could confuse everybody. So I apologize for not bringing this up earlier. So in this setting, I'm simply interpreting the quantum circuit as the cost function itself, right? So you're totally right in being confused or asking this question, because I didn't even mention this. So what we're doing here is we're computing the gradient of the circuit with respect to the parameter. And so what I'm assuming is just that the circuit output is the cost function. So what you get here is something from the measurement, and this is the cost function, and this is the thing we want to minimize. But of course, you can take this random circuit and apply and embed it into another cost function circuit, right? So we can go and we can say like def cost and pass in something, and we can use the random circuit output, and we can say -1, or let me do this, -1 to the power of 2 squared, right? And return this as the cost, for example. And then when we calculate derivatives, we need to calculate derivatives with respect to this function and not with respect to the circuit output. And PennyLane can totally handle this very nicely. So thank you for asking that question, and I apologize for not making it explicit, but in this situation or in this example, I'm just simply interpreting the circuit as the cost function. So yeah.
Okay.
And I think
so
this is
that's
finished
all
running.
Questions which we have. Yeah, great.
Okay, perfect, good timing. So then now we can finally just plot this picture. And what I'm doing here is I'm plotting on a log scale, and I'm doing the qubits on the x-axis, and here is the derivative of the, so E is the cost function here, it should be a C. And yeah, so this is the derivative of the cost function with respect to just the first parameter, and it's the variance around this derivative. So all these samples, the variance of the gradients. And you can see that this is like linearly decreasing on the log scale, so it's going down exponentially fast. And this is just a line of best fit that's plotted over it. So the blue line behind this orange line is the actual values. And so we can see that as we start to increase the qubits in our model, then we start to run into this vanishing gradients problem, and this is yeah, quite bad. So this is an example of a Barren plateau model. So when you're designing your quantum neural network or your quantum circuit, and they rely on variational circuits and variational architectures, I think one must just be very, very careful on the performance of these models when you start to have a very high depth circuit. So when you start to go to a lot of qubits in your model, and you need to make sure that you are not running into these problems. So a lot of architectures for quantum neural networks, I put up a few last week. So this idea of dissipative quantum neural networks argue that their model is really robust and really, really good, but it was then later shown that it falls into Barren plateau problems when you start to scale it. So yeah, I think these are design issues, and I think that we will overcome them. But yeah, we just need to be cognizant and aware of some of the problems that come up in these quantum neural networks and these quantum models. So now I will stop talking and thank everybody for attending again. And I see we are just now finished with time. So yeah, thank you, Francesco, and thank you, Ilya, for orchestrating these events and helping. And yeah, I really appreciate it, and I had a lot of fun.
Yeah, Amira, thank you very much. And I think I'm speaking for everybody. We had lots of fun too. So thank you very much. Ilya, are there more questions for Amira?
There is no questions in Q&A. There are a couple of administrative questions in the chat. Okay. Yes, so which are related. What are the deadlines for the quizzes and what is the deadline for the last quiz? So I don't know, do you want Francesca to say what you think?
The idea of the quiz is that it should take, and Amira will correct me because she prepared it. It will probably take a few minutes to answer. So I don't know, tomorrow. Yeah. The idea is just to compile it after the talk. That was our intention. So there is no real deadline. Yeah. So as soon as possible, I would say. Yeah. No, because the idea is that we don't want you to prepare for the quiz. We want you to take the quiz just after the talk. So that's the plan. Yeah. Okay. I hope that answers that.
There was also a couple of questions. One is now in Q&A, and probably Francesco, you as the interim director of NITheP could answer that. I just want to ask about the type of research that you are doing in NITheP in quantum computing or quantum technologies. Which subfields are you focused on? Quantum algorithms, application, etc. What about are you getting the applications of the postgraduate careers and so on and so forth? And there was a similar questions, yes. If we would like to apply for a PhD in quantum machine learning or quantum computing in general, how can we approach the possible supervisors?
That sounds like the topic for another talk. I think that the best thing, if you are really interested in continuing your studies in quantum computing and related fields, just drop us an email. You can email me, or you can email Amira, you can email Ilya, and we can start an interaction and making a plan. Yeah. If there are, every year there are calls for bursaries from NRF, from NITheP, from other sources, yeah? And we will be happy to coach you in doing that. Yeah. And otherwise, you're most welcome to look at our website, the NITheP website, or our quantum website at UKZN. I will maybe, Ilya, if you could, while I talk, you could type the web link in the chat. Yeah, and or you just go to Google Scholar and you Google us and you see more or less what we are working on. Yeah, but essentially through the lectures of Amira, you have a good overview of what we're doing in quantum machine learning. We're also doing some work on quantum simulation of stochastic processes and similar topics. We are looking at quantum effects in biological systems and many other things. But please, if you are interested, just drop us an email and we can see it from there.
Okay, and there is a question from Graham to Amira, I assume. Yes. Could it be possible that introducing noise into the variational circuit could help with the Barren plateau problem? Thanks.
Yeah, it's such a good question. So I think this has already been tried in some papers, and I can send them to you, Graham. But I think no, because so classically, I mean, this idea of having some stochasticity in your learning algorithm is really beneficial, right? I mean, this is why stochastic gradient descent does really well, because you help to get out of local minima and find a global one, hopefully. But in the quantum setting, I think these Barren plateaus are just something innately different. And so by introducing noise into the model, your algorithm's not learning still. It's still not able to update parameters in a meaningful way. It's just kind of adapting to noise. And so your model still doesn't converge to something meaningful. So unfortunately, I don't think so, to the best of my knowledge, that this can work.
Okay, thank you.
Cool.
Okay, if there are no more urgent questions, then Amira, thank you very much again for the very nice lectures and for suggesting to organize such a school. Thank you very much. And thank you also to the participants for being so loyal over 4 weeks. It's quite a commitment to attend 4 weeks in a row. That's really much appreciated. Thank you, Ilya, for moderating the questions. And I'm not sure whether the announcement of the next mini school came already out, but next week we will start with a new topic. And this time the topic will be classical and quantum chaos. Yeah, so if you're interested in that, please join us again next week. But you will probably receive the announcement, otherwise you will find it on the NITheP website. So thank you very much, everyone. Have a nice rest of the day. And please keep staying safe and on the cautious side, because even if we're at level 1, the virus is not on holiday. Yeah, so be careful out there. Yeah, thank you. All the best. Bye-bye. Thank you, Amira. Yeah.
Bye-bye.